Okay, good everyone. Now I will discuss to you about the General Purpose Graphic Processing Units, Chapter 19. Okay, um, what is GPGPU? GPGPU is a graphics processing unit that is programmed for purposes beyond graphics processing, such as performing computation typically conducted by a central processing unit or CPU. GPGPU, also known as GPGPU computing, refers to the increasingly commonplace modern trend of using GPUs for non-specialized computations in addition to their traditional purpose of computation for computer graphics. Incorporating GPUs for general purposes enhances CPU architecture by accelerating portions of an application while the rest continues to run on the CPU, ultimately creating an overall faster, high-performance application by combining CPU and GPU processing power. Harnessing the power of GPUs for general purposes can be accomplished via parallel computing platforms, which allows software developers and engineers to access graphics cards and write programs that enable GPUs to manage any task that can be para, um, parallel. So that's why. So next is there are motivation about the GPGPU. Discrete GPUs in the system. So this is the system of GPU. So Intel and core. Next is core count and NVIDIA. So all cores are not what is all all cores are not created equal. So meaning to say all the cores is not created equal. So need to understand the programming model. So okay, NVIDIA revolutionized the GPU and accelerated computing in 2007 with its creation of the Compute Unified Device Architecture or CUDA, the fac- the factor computing language for image processing and algorithms. This is the GPU architectures and video, but okay, I nakalimutan gamay. So with those GPGPU. Writing GPU-enabled application requires a parallel computing platform and application programming interface that allows software developers and software engineers to build algorithms. Algorithms algorithms to modify their application and map types of memory in a memory hierarchy for designers to optimize their programs. GPGPU memory optimize their programs. GPGPU memory is used for transferring data between device and host. Shared memory is an efficient way for threads and the same block to share their runtime and data. A GPU database uses GPU computing, compute GPU computing power to analyze and return results in milliseconds. So that's it. The how to use a GPGPU. Okay, this is system and then Intel Core and NVIDIA architecture, NVIDIA GQ110 architecture. These are architectures. This next is CUDA programming model. Okay, programming model or single instruction multiple data thread. All threads execute the same instruction. Okay, the CUDA platform is a software layer that gives direct access to the GPU's virtual instruction explicit and parallel computational elements for the execution of compute kernels designed to work with programming languages such as C++ and Fortran CUDA, an accessible platform requiring no advanced skills in graphics programming and available to software developers through CUDA, accelerated libraries, and compiler directives. CUDA-capable devices are typically connected with a host CPU, and the host CPUs are used for data transmission and kernel invocation for CUDA. CUDA for GPU accelerates a wide uh, variety of applications, including GPU AI, computational science, image processing, numerical analytics. The CUDA toolkit includes GPU, accelerated libraries, and or a compiler, programming guides, or API references, and the CUDA runtime. Okay, CUDA thread hierarchy. Each thread uses IDs to decide what data to work on. So, every each of thread is uses IDs to decide what data to work. So nagkinahanglan siya og IDs na para makalize kung unsa ang iyang pag-work. So that's it. Okay. Next is there are a three-dimension hierarchy: thread, block, and grid. Okay. A group of threads is called a CUDA block. CUDA blocks into a grid. A kernel is executed as a grid of blocks of threads. Each CUDA block is executed by one streaming multiprocessor or SM and cannot be migrated to other SM, or streaming multi-SM can run several concurrent blocks depending sources, or streaming multiprocessor can run several concurrent CUDA blocks depending on the resources. Each kernel is executed on one device, and CUDA supports running multiple kernels on a device at one time. CUDA defines built-in 3D variables for threads and blocks. Threads are indexed using the built-in 3D variable 3D IDEX. Three-dimensional indexing provides a natural way to index elements and vectors, matrix, and volume, and makes CUDA programming easier. Similarly, blocks are also indexed using the inbuilt 3D variable called block IDX. Next, vector addition. So let us assume, let's assume the n is 16, block them is 4 blocks. So this is the vector addition. Next, vector addition, CPU program. So this is how you code the vector addition: CPU program and GPU program. GPU architecture basics. So this is the GPU architecture basics. Execution of a CUDA program. Blocks are scheduled and executed independently on SM or SMs. All blocks share memory. Okay. To execute any CUDA program, there are three main steps. Copy the input data from host memory to device memory, also known as host-to-device transfer. Load the GPU program and execute caching data on chip for performance. Copy the result from device memory to host memory, also called device-to-host transfer. So that's the execution of a CUDA program. Executing a block of threads. Execution unit or warp. a group of threads, 32 for NVIDIA GPUs. Blocks are partitioned into warps with consecutive thread ID. So this is the black 128 SM, so black Jaro 128 block 1. Okay. Execution block of threads. A thread is the unit of execution within a process. A process can have anywhere from one thread to many. So that's the executing a block of threads. Next is a warp execution. So this is a warp executes one common instruction at a time. Threads in a warp are mapped to CUDA cores. Warps are switched and executed on SM. Handling branches. This is the handling branches. CUDA code and there are if true for some trades, else true for others. What if trades takes different branches? Branch divergence. Okay. Branch divergence occurs within a warp. All branch conditions are serialized and will be executed. Performance issue. Low warp utilization. Okay, if and else, if so we are idle trades, and also okay, branch divergence, divergence. This is the branch divergence. Mm, branch divergence. Okay, the divergent branch source level experiments. Um, experiments examines every section which me branch and count how many times each branch was taken by trades in the warp, not taken by any trades in the warp, or diverse divergent branches cause inefficient additional resources and should be avoided by making of trades in a warp branches. Okay, this is a vector addition, so this is we'll tackle early. Yeah, okay. This is example of vector add on GPU. So this is a CODA, then assembly, PTX, example vector on GPU, N is 8 threads in one block, warp size 4, executions. The second, and next is the this is the execution sequence. The next is okay, this is for the last, and this is for the last in study guide. We outline the terms straight black warp and SMT with example. Understand the vector addition example in enough detail to know what S operations are at. So all the topic is covered by CUDA, branch divergence, kernel, OpenCL, stream multiprocessor, trade black, and that's all. Thank you.